Hey everyone, welcome to today's Explainer. Think of this as our ultimate peer study group session for the big chemistry exam. We are going to tackle chemical equilibrium together, and we're jumping right in because there is a lot of ground to cover. By the end of this, you are going to walk into that test feeling completely confident. Let's do this.
Okay, here's our study plan for today. First, the big idea, dynamic versus static. Second, physical versus chemical systems. Third, real world, biology and industry. And finally, we'll wrap it all up with the math and practice problems.
All right, kicking things off with Section 1, the big idea, dynamic versus static. Let's totally shatter the illusion that equilibrium means nothing is happening.
Now, you might be wondering, wait, so equilibrium isn't static? Honestly, it's a trap so many of us fall into. We think equilibrium just means the chemical reaction completely stops. And it's a perfectly fair question, right? Because on a macroscopic level, it looks completely dead. You stare at a beaker and absolutely nothing is bubbling, nothing is changing color, nothing is reacting. But the reality? It is way more active than it appears.
Here is the absolutely crucial point. Dynamic equilibrium is a state where opposing processes occur simultaneously at the exact same rate. That means there is zero net change in the measurable amounts of reactants or products. But if you zoom in, those individual molecules are frantically moving back and forth across the phase boundary. They are working in overdrive, but they're just perfectly canceling out each other's progress.
To really visualize this, imagine a two-cylinder water transfer activity. Let's say you fill cylinder 1 with colored water. Then you grab two glass tubes and use them to simultaneously scoop and transfer water back and forth between cylinder 1 and an empty cylinder 2. What happens? Well, you constantly move water back and forth until the water levels equalize and become totally constant. It brilliantly illustrates how forward and reverse rates achieve a perfect balance. The water is literally still moving through the tubes, but the level, which represents our chemical concentration, never actually changes.
And we actually know this dynamic motion never stops because chemists literally catch the molecules in the act using isotope tracers. Take the synthesis of ammonia. If you start the Haber process with heavy hydrogen, an isotope called deuterium, instead of regular hydrogen, and let it reach equilibrium with nitrogen, you get ND3. Now, if you mix that with a standard hydrogen and ammonia equilibrium mixture, you don't just get two separate untouched pools of molecules. When chemists analyze the mixture, they find mixed isotopes, like NH2D. This is absolute irrefutable proof that the molecules keep reacting and swapping atoms even at the equilibrium stage.
Moving right along to Section 2, physical versus chemical systems, let's see how physical phase changes stack up against actual chemical equilibria.
If we look at a physical change, like evaporation, we can track it by placing a watch glass of water inside a closed, transparent box hooked up to a manometer. At first, you'll literally watch the mercury level rise as the water evaporates into the dry air, adding gas molecules. But eventually, you'll see the pressure level out and just flatline at a constant value. The evaporation hasn't magically stopped. It's just that the rate of vapor molecules condensing back into the water now exactly equals the rate of molecules evaporating out of it. Now, check out the sharp contrast here between solid-liquid and gas-liquid dissolution. It's super interesting. Think about a totally saturated sugar solution. It's a dynamic solid-liquid equilibrium, where the rate of the solid sugar dissolving perfectly equals the crystallization rate. Compare that to a gas dissolving in liquid, like carbon dioxide in a bottle of soda. That's governed by Henry's law, which says the gas solubility is directly proportional to the pressure above it. The second you crack open that bottle, the pressure drops, the equilibrium shifts completely, and the CO2 fizzes out, trying to reach a new balance with the room's atmosphere.
Here's a fantastic summary table contrasting the different traits of physical equilibria. You'll definitely want to screenshot this for your exam review. Notice how each physical process has a measurable constant property at equilibrium at a given temperature. For liquid vapor, it's vapor pressure. For solid liquid, it's the melting point. And for dissolution, it's concentration.
And whether we're talking about physical phase changes or complex chemical reactions, the rule stays the exact same. The reactant levels just flatline once equilibrium hits. The forward and reverse reaction rates balance out perfectly. In fact, those two rates must be absolutely equal for the system to be at equilibrium.
Okay, guys, Section 3. Real world, biology, and industry. Let's talk about why this actually matters for life, death, and massive industrial profit.
In our own bodies, equilibrium literally dictates survival. Hemoglobin binding with O2 is a critical equilibrium for transporting oxygen from our lungs straight to our muscles. That is life.
But on the death side, hemoglobin also binds with carbon monoxide molecules. And because carbon monoxide binds so much more strongly, it actually outcompetes the oxygen, shifting the balance entirely and creating a highly dangerous toxic equilibrium state that starves your cells of oxygen.
On the profit side of things, industrial chemists have to optimize reactions like the Haber process for synthesizing ammonia, which, is used globally for fertilizer. The ultimate goal? Maximize product yield while minimizing energy expenditure. They do this using Le Chatelier's principle, which basically states that systems will always counteract changes in pressure, temperature, or concentration. For ammonia, cranking up the pressure shifts the equilibrium to the side with less gas volume, which happens to be the ammonia side. Then, by continually liquefying and removing the ammonia product as it forms, they force the system to just keep driving the forward reaction to replace it. It's brilliant, ensuring continuous profit.
All right, home stretch. Section 4, Math and Practice Problems. Time to get you ready for the final exam.
The math here actually goes way back to 1864 with the Law of Mass Action by Cato Goldberg and Peter Waage. They defined equilibrium through this historical viewpoint of active mass, which today we just simply call concentration. They proposed that the concentrations in an equilibrium mixture are constantly related by a specific equation, no matter what amounts you actually start with.
Which brings us to the equilibrium constant, or Kc. Think of this like the final score in a massive tug-of-war match between the right side and the left side of the equation. It helps us visualize the ratio of products to reactants. Specifically, it's the product of the concentrations of the reaction products raised to their stoichiometric coefficients from the balanced equation divided by the reactants raised to their stoichiometric coefficients.
Now here is a massive exam tip. If you alter the chemical equation, you have to change the math. Take hydrogen and iodine synthesizing into hydrogen iodide. If you multiply the entire chemical equation by a factor of n, your new mathematical constant becomes Kc raised to the power of n. And if you reverse the reaction entirely, looking at it right to left, your new constant is simply 1 over the original Kc. You absolutely need to remember how changing those coefficients alters the math.
Okay, let's actually practice this. Say we're synthesizing ammonia from nitrogen and hydrogen. Let's say at equilibrium your N2 concentration is 1.5 times 10 to the negative 2, H2 is 3.0 times 10 to the negative 2, and NH3 is 1.2 times 10 to the negative 2. Feel free to pause the explainer right here if you want to calculate this yourself. Okay, if you plug those numbers into the products over reactants formula, remembering to square the ammonia and cube the hydrogen based on the balanced equation, your calculated Kc will be exactly 355.
Finally, we've got heterogeneous equilibria. These usually involve pure solids or liquids. The golden rule for your exam: the concentration of pure solids or liquids is essentially constant, so it gets completely omitted from your math. Left out entirely. For sparingly soluble ionic salts, we use a specific constant called the solubility product constant, or KSP. So for solid barium sulfate dissolving into barium and sulfate ions, the KSP expression is literally just the concentration of barium ions times the concentration of sulfate ions. The solid barium sulfate? Completely ignored in the equation.
As we wrap up today's explainer, I want to leave you with this thought. If equilibrium governs everything from massive industrial fertilizer profits to the very oxygen binding in our blood, how might subtle, even tiny changes in our environment ultimately shift the balance of life itself? Think about how Le Chatelier's principle applies to the entire world around us. Good luck on your exams, keep studying hard, and I'll see you in the next one.